situation where the spin-orbit interaction is very weak, so that we can turn it off. And that happens if you have, materials that are made out of light atoms where the electrons never go fast enough to experience the relativistic effects that give you the spin-orbit interaction. So if that's the case, if you can ignore the spin-orbit interaction, then then effectively you have a symmetry which is under rotation. You can independently rotate spin. And so then you can combine this spin rotation with the real time reversal operator to give you a time reversal symmetry which is just complex conjugation. It doesn't rotate the spin. And that squares to +1. Okay, so if you have this extra symmetry, which is spin rotational symmetry, then you can have a time reversal squaring to +1. And so it's the same story with the particle-hole symmetry, I think. So the intrinsic particle-hole symmetry squares to +1, but if you have spin rotational symmetry, then you can have it square to -1. Okay. All right. Okay. So for topological superconductors, we have this I want to say a little bit more about these Majorana zero modes these discrete Majorana zero modes. There's something, of course, we very much would like to make come to life in the real world, the reason for that is this brilliant insight that Alexei Kitaev had, which is that the degenerate states that you have due to a pair of these discrete Majorana zero modes can give you a method for storing and manipulating quantum information. Okay, and so again, the idea is that two of these separated Majorana bound states defines a single Dirac fermion, if you will, which has two states. It can either be occupied or empty. Okay,
when you do the BDG transformation, it seems that the chiral symmetry is always there automatically.
No. The symmetry that's always there when you do BDG is the anti-unitary. It's the particle. It's this one. So in general, if you don't have time reversal symmetry, then you don't have to have the chiral symmetry in a topological superconductor. So in D3 you do have the chiral symmetry, but in class D, which is a superconductor without time reversal symmetry, then
so in BDG you always have the particle hole symmetry, right? Once you do the BDG rewriting of the Hamiltonian, right?
yeah. So the Hamiltonian at K is then related to the Hamiltonian at minus K by the particle hole symmetry. Right. So the point is that the intrinsic symmetry that you have is a anti-unitary symmetry that involves complex conjugation.
Right. So how is it then that some states cannot have this particle hole symmetry? I mean, it seems to me, maybe I'm missing something, but it seems to me that once you rewrite it as BDG, you always have this thing.
Well, no. So you always have there's always you do have a positive energy state has a partner which is a negative energy state. But there's sort of two ways you can make that happen. You can either make it happen by having a unitary operator that anti-commutes with your Hamiltonian, or you can have an anti-unitary operator that anti-commutes with your Hamiltonian. Okay, and those two are different. Okay, and that's the chiral symmetry is the unitary operator that anti-commutes with the Hamiltonian, whereas the particle hole symmetry is the anti-unitary operator. So and those are two different cases.
I'm a little anxious. Just what is this the K theory of?
Ask Greg. Yeah. So or ask maybe Professor Witten will be able to explain that to you. So I only have a very dim understanding of what K theory is. So I don't want to. I think I would probably say something that's wrong if I tried to answer that. Yeah. I'm sorry. Speak louder. Yeah, that's. I think there's a historical. I'm not sure exactly what the history of that name is. So I think it has something to do with the chiral symmetry and the Dirac equation, but I don't have a good answer for that, for why that nomenclature. Yeah. Yes?
How many of the possibilities in this table have been realized?
Well, so certainly, so it depends what you mean by realized. Okay, so there's realized in theory and there's realized in experiment. So let's see. I don't know if I have all these in my head or not, but certainly class A, and so class A1 is if you have something that has very weak spin-orbit interaction. So that I think you can approximately realize, to the extent that you can set the spin orbit to 0. And then, so class D, I think we, now of course there's a question as to whether we have realized the non-trivial topological classes of these. Okay, we would like to think that we have, but that's still under debate. Class A2, I think we're in we're under, that's under control. Now there are other ones. So for instance, these ones, you could imagine having superconductors that have spin rotation, that don't have spin orbit. Okay, and so I think there are things that you can do there. So for instance, it may be possible to have these. Now, I don't think there are any experiments. I'm not sure there are experiments that talk about these. So, yeah. So, all right, good. All right. Okay. So let me just say that. So Kitaev's insight was that if you have a bunch of these well-separated Majorana modes, say 2n of them, then that's a way of storing n qubits of quantum information. Okay, and the beauty of this is that if the Majorana modes are well separated from each other, then the quantum information is stored non-locally, which means that if you just look at one of them, okay, then you can't measure the state that that qubit is in. Okay, and so this, and this is the whole problem with trying to make a quantum computer, is to try to keep the quantum computer from accidentally measuring itself. Okay, and so in principle, if you can store the quantum information in these well-separated, Majorana modes, then you can protect the quantum information from sort of local sources of decoherence. Okay, and so that's the dream, that we can do that, and then one can do even a little bit more, which is that if you can find ways to sort of braid these zero modes around each other, then you can manipulate the states that you have. Okay, and that's sort of, so you can do a unitary operation on these qubits that you have. Okay, and that's sort of what you'd want a quantum computer to do. You want to have it store information, then you want it to perform unitary operations on this. Now, unfortunately, with these Majoranas are a little bit too simple. So even if you could make these work, the operations that you can do are not powerful enough to make a universal quantum computer. Okay, but I think they'd be a good start. So we very much like to make these happen. Okay. Yes.
Can you explain how the method for the gradient change the state? Because that was the gradient change the state.
How do I get from this to this? Yeah, so it's basically contained in this rule. So the idea is that if you exchange two Majoranas, then one of them goes to the other, but the other one goes to a minus sign. And the reason you have that minus sign is because if you think the Majorana is like a vortex, so a fermion going around that vortex picks up a minus sign. Okay, so I can think of a vortex as being connected to a string around which the fermion picks up a minus sign. And so if I do an interchange between them, I think you can convince yourself that one of them is going to cross the string and not the other. Okay, and so that's the origin of this minus sign, and so there's a little bit of, you have to go through a little bit of algebra to see that this interchange rule sort of gives you this transformation. I don't think I can't do that on the top of my head right now, but it follows from this. Okay.
So, what are the sources of local incoherence?
Interaction with other degrees of freedom.
And they're always local.
Well, so we like to think that that physics is local. Okay, but of course, there's local and there's really local. Now how these things are local to the extent that they're the wave functions of these modes we think decays exponentially. Okay, now e to the minus 10 isn't that small, right? So I think there's a practical concern of how local does local have to be in order to make this work, okay? And so I think that's a practical question. If anything like this is ever going to work, that practical question is going to have to be addressed, head on. Okay, but what we can say is that exponentials get really small when you make them really far apart, and if you're able to separate them by a really long way, then the exponential is going to save you. But so the practical question is in a realistic setting, they're not going to be miles apart, right? So how good is good enough? And that I think is a practical question that needs to be addressed. Yeah.
Question on the last sentence. Is there an easy way to see that? Does that have to do with some irrational number?
Yeah, it basically has to do with the fact that these kinds of operations, so you think of, when you do operation on a qubit, you can think of doing a rotation on the Bloch sphere. So the state of a qubit you can think of is like a spin. It's a vector on the Bloch sphere. So these kinds of rotations, they only allow you to do rotations by 90 degrees. Okay, and so you can't get everywhere by just doing 90-degree rotations.
Is it obvious that the only rotations non-abelian braiding allows you to do are 90-degree rotations?
Well, it's because of these. It's because of this rule. This is all you can do. Yeah. All right. Okay, let's see. So I have 15 minutes. Is that right? Okay, good. All right. So, okay, so look, so this is something we very much would like to make happen, and this is something people are trying. So how can you make these Majorana fermions come to life? So actually, originally, there's proposal by Moore and Reed, and the idea that this could arise in the fractional quantum Hall effect. Okay, and so this is really where some of these ideas, were first thought about, and so there are experiments in the nu equals 5/2 fractional quantum Hall effect, which sort of look like what you'd want to make happen, and so it might be that this is indeed a venue for these Majorana fermions. But in terms of these superconducting topological superconductors, so one thing one can do is one can try to, one of the problems is we're not given topological superconductors. Okay, so there are various proposals for how one might be able to find unconventional superconductors that have topological superconductivity, and this is something which I think is not. We don't have definitive examples of those. So another idea, though, is that, what if we just use an ordinary superconductor, but we combine it with some other kind of material that has some topological properties? Okay, and so they're using, and we can induce superconductivity in that other material using the proximity effect. And so here there's been a fair amount of effort So there's an idea that you can, if you can make the surface of a topological topological insulator superconducting, then you get something like topological superconductivity. And then there's ideas that one can, you don't even really need a topological insulator. You can do it with semiconductors and in particular quantum wires or ferromagnetic atomic chains. And it's these ones which have had a lot of promising experimental developments. And so I'm just going to say a few words about those. So the idea, so Zahid mentioned this a little bit yesterday, but let me just say that there's something special about the surface of a topological insulator. So remember, let me remind you, the thing that's special about a P plus IP superconductor, so remember a P plus IP superconductor was this a two-dimensional topological superconductor which has the Majorana modes at a vortex. And so the thing that's special about that is that you have a Fermi surface, but you have spinless electrons. So there's just a single state for electrons going around the Fermi surface, and then I'm pairing the states at k and minus k. Okay, and I'm pairing them with a P plus IP type order parameter, and that gives me this topological superconducting state. Now, an ordinary superconductor is different from this, though, because an ordinary superconductor has spins up and down, which are paired into a singlet. Okay, and so an ordinary metal has two Fermi surfaces, one for the up spins and one for the down spins, and they're sort of paired to each other in a singlet, and that gives you, that's sort of like two copies of this, if you will, and that is not a topological superconductor. Okay, but if you look at the surface of a topological insulator, if you are able to make it superconducting, so now you can make it superconducting. You're pairing. So the surface of a topological superconductor is only half of this, but it has the up spins and the down spins on opposite sides, and so you can do a singlet pairing of these, but you still only have half. And so this is sort of like this, okay? And in fact, it supports these Majorana zero modes at vortices, okay? And so the idea then is that by using this surface of a topological insulator, if you have an H over 2E vortex, in fact, you have this Majorana zero mode bound at this vortex. Okay, and there are other ways you can do this too. If you instead take the two-dimensional quantum spin Hall insulator, okay, then you have the helical edge state of this of the quantum spin Hall insulator, and you can gap that with a superconductor, or you can gap it with a magnetic gap. And on the boundary between these two, then there will be a Majorana zero mode. Okay? And so this is sort of like the one-dimensional topological superconductor. Okay? There's a difference, though, which is in the one-dimensional topological superconductor, you actually have to break time reversal symmetry, okay, in order to get the Majorana mode. And the superconductor itself breaks time reversal. Here, the superconducting state doesn't break time reversal, but it's the insulator on the outside that does break time reversal. Okay, and so this is sort of a complementary situation to the one-dimensional topological superconductor. Okay, so there are other things you can do. So you can make, so if I look at the surface of a three-dimensional topological superconductor on an interface between a superconducting gap and a magnetic gap, then there will be a one-dimensional channel, which again carries which is sort of like the edge of a two-dimensional P plus IP superconductor, and so this has a chiral Majorana mode. Or you can have a, sort of a Josephson junction between between superconductors. And then when the phase difference is equal to pi on this Josephson junction, then you have sort of a non-chiral Majorana mode when the phase difference is equal to pi. So there's different sort of ways that you can introduce these sort of topological superconductivity in these topological insulator type structures. Okay. Now, so an important insight. So this this idea, I think that you could do it with a topological insulator. That was sort of the first idea that you can use a proximity effect. But shortly afterwards, it was realized that you don't really need the topological insulator. What you